Okay, let's continue. Okay, so this is the second part of the talk where I'm giving further examples of cross compositions or compositions, and also giving some additional features of this whole framework. Okay, so the first idea, the first thing I want to talk about are those PPTs, or polynomial parameter transformations, which is a very simple concept, namely in NP hardness or ETH hardness or W1 hardness or any hardness complexity theory, yes, you can transfer hardness results by reductions, right? So why not kernelization hardness? Yes, meaning the idea is that if you have a problem about which you know that there is no polynomial kernel, and you know that there is a problem that is harder, for appropriate notion of harder, then the other one should also not have a polynomial kernel. Yes? And now it boils down to finding the right notion of a reduction. So this is polynomial parameter transformation. So suppose I've got two parameters problems, P and Q. Yes? And a polynomial parameter transformation from P to Q should be an algorithm, maybe I'll write it here, that takes an instance of P, returns an instance of Q that should be, as usual, equivalent. Yes, this is an yes instance of P if and only this is a yes instance of Q. And so maybe I can draw it like this. Here's a box, here is a box. So this belongs to P if and only if this belongs to Q. Yes, and what should be so special about this reduction? It should run in polynomial time, because at the end of the day we are now dealing with polynomial time algorithm, being kernelization. And also the parameter blow-up should be polynomial. Yes, so the output parameter should depend polynomially on the input parameter. Yeah, so if I've got here parameter k, here there should be parameter poly of k. Yes. And now a sort of a symbol pushing lemma is that if you have such a reduction from P to Q, and you know that P doesn't admit any polynomial compression algorithm, yes, so any polynomial compression into any language R, then neither does Q. Why? Because if Q had such a compression algorithm, then you could compose this reduction with the compression algorithm to give a polynomial compression for P. Yes, the same as always with the hardness reductions. Good. So this is a way of transferring hardness of kernelization. So let's give one example. So the example I will give will be a STEINER tree problem, actually the node variant of the STEINER tree problem. We are given a graph with some terminals. These are these yellow boxes. Yes, these are special vertices. And I would like to connect those special vertices as cheaply as possible in the following way. I want to find a subset of vertices X, subset of non-terminals X, such that the terminals together with this set X induce a connected graph. Yes, so I want to buy as few vertices as possible, yes, in order to connect all the terminals with each other. Yes, so this is an example. The parameter I will be concerned about will be the budget, so the number of vertices I can buy, plus the number of terminals. So the total size of the tree that I get at the end, the subgraph that I get at the end. Yeah? Good. So we now show that a STEINER tree with this parameterization doesn't have a polynomial kernel unless bad stuff happens. So now from now on, I will just replace it with 3 dots. Good. So the idea is to define a auxiliary problem, yes, and then give a polynomial parameter transformation from this auxiliary problem to my problem of interest, being the STEINER tree problem. Okay, so this is the general methodology, sort of. We introduce a simpler problem, like maybe not simpler in terms of being in lower complexity class, but sort of conceptually simpler, that is trivially compositional, yes, but it sort of encodes the hardness of the original problem. Yes, and then we sort of embed this hardness by a PPT reduction. Yes, from my auxiliary problem to my target problem. So the idea is that in this definition of this auxiliary problem, we sort of extract the reason for hardness, yes, of the target problem. We prove that it is compositional, and using the combinatorics of the new problem, this is simpler, yes. And then we sort of embed this instance into the target problem, showing that actually the target problem is at least as hard as the original one. Yeah? So this is the motivation, blah, blah. But now let's look at that example. So the auxiliary problem that I will work with will be called colorful graph motif. It works like this. I've got a graph G together with a coloring of its vertices in k colors. This may be not a proper coloring. For example, here I have two red nodes that are next to each other. Yes? Here are actually four colors. There's green, yellow, red, and blue. And the question that I ask in this problem is whether I can find a connected subgraph of this graph that has one vertex from each color, exactly one from each color. So for example, this is a solution because it has one green, one red, one yellow, and one blue vertex. Right? Okay. So this problem, I will not prove it. It's a nice exercise to show that it is NP-hard even on trees. Yes? So it's a hard problem. Just a remark, this problem is FPT, and there is a lot of very nice algorithms for this problem using algebraic approach. So if you are interested in this problem, if it caught your attention, it's nice to see what happened there. But it doesn't admit a polynomial kernel unless bad stuff happens, because it has trivial composition. I take just the disjoint union, but I reuse the colors. So the color red in the output instance is the union of color red in the input instances. Yes? And then a graph has such a colorful connected graph motif, yes, if and only if one of the connected components had, yeah, because it needs to be connected. Yes? Good, so there is no polynomial kernel for this problem unless stuff happens. So now, well, what I will show is a polynomial parameter transformation from this colorful graph motif to the STEINER tree problem. So this is a reduction from colorful graph motif to the STEINER tree problem. So let me start with the instance of colorful graph motif. It's actually exactly the same instance that we had on the previous slides, just drawn in a slightly different way. What I do, I add one terminal per each color, yes, and I just connect it to the color. These black nodes are terminals now. Yes? And I ask whether it is possible to connect all terminals by buying at most k non-terminals. And now observe, each terminal needs to be connected to the others. Yes? So I need to pick at least one guy from each color class. Right? I have only budget k for those connecting nodes, so I need to pick exactly one from each color class. And now, in order to connect them, I need to pick those guys so that in the original instance of connected of colorful graph motif, they induce a connected subgraph. Yes? Simple as it is. Yes? Good. So this is the wrap-up, yeah, already. Colorful graph motif doesn't have a polynomial kernel. We have proven this by a trivial composition. Then it reduces to STEINER tree parameters by k plus t, because in the target instance I've got the number of terminals being the input parameters and the budget being also the input parameters. So k plus t is actually 2k in the original terms. Yes? And hence the STEINER tree doesn't have a polynomial kernel unless bad stuff happens. Because if it had a polynomial kernel, then the composition of the reduction and this would give a polynomial kernel for connected colorful graph motif. And that's the end of the story. Actually, there was before this was shown, there was another composition for STEINER tree that was more conceptually involved. Yes? But what we did here, yes, we extracted the reason why it is hard to kernelize STEINER tree into a pivot problem, yes? Into a problem that encapsulates this hardness. Good, so let me give another example that will actually sort of combine the two examples that I was giving before, namely the pivot the auxiliary problem and the instance selector idea. So the problem that I'm now interested in is disjoint paths, or otherwise named vertex disjoint path. I've got a graph, G, and I've got k pairs of terminals, S1, T1, S2, T2, Sk, Tk. Yes? And now I'm asking whether there's a linkage between the sources Si and the targets Ti. Yes? And the linkage is just a family of paths, P1 up to Pk, such that each Pi goes from Si to Ti. Yes? So each path has a prescribed source and target. Yes? So now this problem is NP-hard in general, but it is fixed parameter tractable by a very non-trivial argument that essentially is one of the most important algorithmic results of the Graph Miners project of Roberts and Seymour. And now we will show that it actually doesn't have a polynomial kernel. Yes? Unless stuff happens. So this example that I will show is due to Bodlander, Thomas, and Yeo, and it was proven shortly after the composition framework was introduced. Okay, so the auxiliary problem will be quite funny. It will actually have nothing to do with graphs. It will be a problem on words. Yes? So I've got a word W over some alphabet on the input, and the alphabet has k letters. The size of the alphabet is my parameter. Yes? So I've got a long word, say like this. Yes, this is a word over 4-letter alphabet consisting of A, B, C, D. Yes? And now I ask, can I find disjoint subwords of this word? Yes? U1 up to UK, such that each UI starts and ends with letter AI. In this example, here, I've found one subword that starts and ends with B, one subword that starts and ends with C, one that starts and ends with A, and one that starts and ends with D. Yes? And they need to be disjoint. Right? Good. So this is the disjoint factors problem. It is NP-hard. I will again not prove it. And now we give a cross composition from the disjoint factor to itself. Yes, so formally from the unparameterized disjoint factors to parameterized disjoint factors. Yes? And because it is NP-hard, it will show that disjoint factors themselves do not have a polynomial kernel or polynomial compression unless bad stuff happens. Okay, so the input to the composition is a sequence of words, W1, W2, WT, over the same alphabet. Yes? Again, I can group the instances according to the alphabet size. Yes, so I can assume that the alphabet size is always the same, so I can think of all the words as over the same alphabet. Yes? Good. Okay, so again, copying instances yields that I can assume that the number of instances is power of 2. Yes, so L is the logarithm of the number of instances. Yes? So now I will extend my alphabet a bit. I will add L, so log T, new symbols. D1 up to DL. Yes? So observe that in this manner, the new parameter, the size of gamma, the new alphabet, is the old parameter sigma. The old size is bounded by the maximum instance size in the beginning sigma, plus log T. Yes? Which is allowed, yeah, in a cross composition. Okay, so now from W1 up to WT, we construct one word W as follows. So suppose now that L is equal to 3, so I've got 8 words on the beginning. First, let me look at letter D1. I do the following. When I will make this one large string, I will introduce D1 in 3 positions, at the very beginning, in the middle, and at the very end. So if D1 is only on those positions, observe what happens. In order to find a factor that starts and ends with D1, I need to basically either cross out the first half of the word or the last half of the word. Right? And I have a choice of 2. Then for D2, I will do the same but in halves. Yes? In the first half, I will put in the very beginning, in the very end, and in the middle. And the same in the second half. So now if I crossed using D1, if I used the second half of the word for the factor for D1, yes, I've got like a fractal situation here. I can here either cross out the first half of the first half or the second half of the first half. Yes? And the same for D3. Yes? So now by making these choices for D1, D2, D3, yes, you can see that basically D1 crosses out half of the word, D2 crosses out half of the remaining half, D3 crosses out half of the remaining half, and so on and so on. Yes? So the factors used for D1 up to DL, yes, they cross out all but one of the input words. Yes? And any of the input words can be left in this manner, yeah? Because I can just make it remain. Yes? So now, this is just my output word. Yeah? Because on one hand, yeah, if I have disjoint factors for this word, yes, then actually all of the disjoint factors for the letters from sigma, they must be in one of those input instances. Yes? On the other hand, if one of those input instances has disjoint factors, yes, I can just put them there and steer all those DIs so that I've got disjoint factors for them as well. Right? Good. So again, this was the idea of an instance selector in a sense. Yeah? These additional symbols D1 up to DL were sort of making binary choices, yes, that at the end finalized in setting the index of the instance that needs to be solved. Yes? Good. So the output parameter is polynomial in the maximum input size and the log of the number of instances, which is allowed. So those disjoint factors doesn't have a polynomial kernel unless NP is contained in co-NP/poly. Yes, good. Okay, so the first part is already done. We have shown hardness of kernelization for the pivot problem. So now we need to do the second half, which is a reduction from disjoint factors to disjoint paths. Yes? Okay, so let's start with some instance of disjoint factors. Yes, so this is a word over some alphabet sigma. Sigma is the parameter. Yes? So I now create the following graph. I create a large path with one vertex per each of those letters. Yes? I have colored them so that you can see that basically different vertices correspond to different letters. They are actually not colored in the graph, but it will be convenient to see it on the picture. Okay, now for every symbol of my alphabet, for every letter from my alphabet, I create one terminal pair. Yes, that needs to be joined. So for letter B, I've got SB and TB. For letter C, SC and TC, and so on and so on. Yes? And now I do the following construction. I look at letters B in this word, for example. I look at and I index them. One, first occurrence, second occurrence, third occurrence, and so on. Yes? I connect SB with the odd occurrences, and I connect TB with the even occurrences. Yeah? Sounds strange a bit. Yeah? And now observe that if you have now disjoint factors, okay, in other words, if you have now a linkage between SB and TB, yes, then it needs to go first to some odd occurrence, and then travel to some even occurrence, and then go here. And because the path needs to be disjoint, these factors in this word needs to be disjoint as well. Yes? So this gives you a solution to disjoint factors. On the other hand, if you have a solution to disjoint factors, yes, you can always assume that the factor for, say, letter B is spanned between two consecutive appearances of B. Yeah? Because I could always shrink if there was a B in the middle. So it is always spanned between some even occurrence and some odd occurrence, or vice versa. Yes? So this gives me also such a path here, either from odd to even, or from even to odd, the other way around. Yeah? So this means that there is a linkage if and only if the original instance had a solution. So this is a proper PPT reduction from disjoint factor to disjoint path. So the bottom line is that disjoint paths do not have polynomial kernel unless bad stuff happens. Good. Okay, so these were basically the examples I wanted to give of various cross compositions, and now I would like to move to some other features of this whole story. So in the whole composition framework so far, we were just working with OR. Yes, there was OR composition, OR distillation, and so on and so on. And whenever we were combining some instances, yes, into one instance, the resulting instance should represent the logical OR of the input instances. Yes? So the natural question is, what if we replace OR with an AND? Yes? would everything work? Yes? So you could equivalently define AND distillations, and cross-compositions, and so on, by just requiring that the output instance must represent the logical end of the input instance. Yes? And some parameters problems actually have natural end compositions. One example that probably will be more clear after the next lecture is the tree width problem, whether the input graph has tree width at most k. This problem is fixed parameter tractable, and the disjoint union is the trivial end composition, because you just the disjoint union of graphs has tree width at most k if and only if each of the individual graphs had tree width at most k. Yes? So for some time there was this end conjecture, yes, that this backbone theorem that was proved by Fortune and Santana for OR also happens for AND. Namely, if, say, SAT or FreeSAT or any other NP-hard problem for that matter has an AND distillation, then you have a collapse. The problem was that the proof of Fortune and Santana, the original one, it breaks down simply. It doesn't work for OR. Yes? So this was for a few years an open problem. It was finally confirmed by Andrew Drucker in 2012, yes, via a much more difficult proof than Fortune and Santana, but actually also much more insightful proof in some sense. So basically the corollary of all this story is that you can just replace in the whole framework OR with AND and everything works. But the practice is that most problems that we are dealing with actually admit natural OR compositions rather than AND compositions. The number of problems with AND composition is somewhat limited. Good. Okay, so this was about AND composition. So let me now talk a little bit about weak compositions, another variant of composition. So in the morning we have probably shown, yes, there was a kernel for vertex. Okay, there was a kernel. I remember, I looked at the board at some point, yes. So there was a kernel for vertex cover which had 2k vertices. This was this one that was via this LP tools, yes. So this kernel can be encoded in k-square bits, right? By just encoding the matrix. So this is a kernelization into bit size k-square. So the natural question is this optimal? Yes? Can you get sub-quadratic bit size? And the answer is I don't remember what question I actually asked, but the answer to this question here is yes. We can prove that actually quadratic is optimal. More precisely, we can give this framework of weak compositions using which we will show that there is no kernelization into bit size k to 2 minus epsilon for any epsilon larger than 0. And this will be done by this framework of weak compositions, which is basically the technique basing on the same methodology to prove that some problems that have polynomial kernels do not have better polynomial kernels. Yes? So this was first observed by Dell and Van Melke back in 2010, and then it was developed further by other authors. So just to give the credit. Okay, so what is the intuition behind these weak compositions? Okay, so assume that I've got an OR distillation. Yes, I'm back to Fortune and Santana setting, and I've got like a bazillion of instances on the input, say k to 1000. Yes, and now I do OR distillation. Yes, and basically what Fortune and Santana says is that whatever bazillion I put here, I do not have composition into bit size, say k to the 7. Yes, but intuitively, even kernel like OR distilling it to k to 999 should be excluded, yeah? Because even then I would lose some information. Yes? So even if you do OR distillation into bit size that is not just polynomial in the maximum input size, yes? But polynomial in the maximum input size times sublinear in the number of input instances, this should be also problematic. Yes? So, and it is actually true. If you examine the proof, yes, this shows that it also excludes an OR distillation that takes t instances, x1 up to xt, each of size at most k, and yields one instance with bit size t to 1 minus epsilon for any epsilon larger than 0 times any polynomial in k. Yes? And the reason, the intuitive reason why this should hold is put t as super, super large. Yes? Then t to 1 minus epsilon, so like k to like 1000. Then k to 1000 to power 1 minus epsilon will be actually smaller than t. Yes? Because this 1 minus epsilon times this 1000 will not eat up this c here. Yes? So this should be also excluded, and the examination of the proof shows that actually it is excluded. Yes? So let's look again at the proof of the cross-composition framework. Yes? So this was this chart that was already in the previous lecture. Yes? So we start with some instances. We group them according to this polynomial equivalence relation. This is a detail. Yes? We compose them into large instances but with small parameter. We compress them and say that this is a contradiction because we just got an or distillation. So now, suppose that this compression was actually a compression that took an instance with parameter, say, capital K, and yielded something of bit size better than k to the d. Yes? Then if here I relaxed my requirement that this should be poly k to requirement that this should be poly k times t to power 1 over d, where t is the number of instances I start with, yes? Then by composing this function with this function, yes, I would still get dependence on the number of instances being like t to 1 minus epsilon, just scaled by d. Right? Which would also be a contradiction. Yes? So this means that if I have a composition that yields me an instance not with bit size depending polynomial in log t and k, but depending with bit size poly k times t to 1 over d for some constant d, then I actually exclude the compression into better bit size than k to the d. Yes? Because just the combination of two yields the same blow up in the complexity theory. Yes? So now we can define this notion of weak composition. This is exactly the same as our composition, just with this red component substituted. So I say that unparameterized problem Q weakly cross-composes to my target problem L if I can find this polynomial equivalence relation, a real constant D, yes? And an algorithm that takes those many strings on the input, composes them in polynomial time into one instance of L, yes, yx star, that acts as an OR of the input instances, yes, as usual. But the target parameter is not now poly of log t and the maximum input size. It is just poly of the maximum input size and roughly t to 1 over d. You may assume that you have order of 1 here as well. Yes? So this is weak cross-composition. And this constant d that governs this blow-up of the parameter depending on the number of input instances will be the dimension of the cross-composition, of the weak cross-composition. And now if you just go through this whole proof that I have shown in the previous chart, you will get the following result, that if I have a weak cross-composition from some NP-hard language Q to my target language L that has dimension d, yes, then I can exclude a polynomial compression for L into any language R that has bit size better than k to the d. Yes? Good. So just a notational remark, this is usually called weak cross-compositions, but some authors call it compositions with bounded cost. So now, as an example, I will show you that you cannot get a subquadratic kernel or subquadratic compression for vertex cover. Yes? So just to note that actually it matters how we measure the size of the kernel. Yeah? Because in vertices, the kernel has linear size. Yeah, but in bit size, it has quadratic size. Yes? Good. So the crux, as usual in hardness reductions, or as sometimes in the hardness reduction, is to find an appropriate problem to start the composition with. And this example, exactly this proof, is due to Dell and Marks from 2012. Good. So the problem we will start with will be this funny problem called multicolored BICLIQUE. This is just a design of this. The design of this problem is to make the composition convenient. So the input is a bipartite graph, H, where each of the sides is partitioned into color classes, into groups, simply, into K groups. Group number 1, group number 2, group number 1, group number 2. So K is equal to 2 on this graph. Yes? And now I ask whether I can pick one vertex from each group, so 2K vertices in total, yes, so that they form a BICLIQUE. Yes, a complete bipartite graph. So each of those is connected to each of those. Yes? So this problem is NP hard, and you can assume even that each of those groups has the same size. Yeah? Because you can always pad with isolated vertices. This doesn't hurt. Yes? Good. So now we give a weak cross composition of dimension 2 from this problem to vertex cover. Yes? Observe now that here I am actually starting with a different problem that I am ending up with. Yes? And this will be very convenient in the proof. Yes? And this is also provided by the cross composition framework. Okay, so we can do this polynomial equivalence relation business, so we can assume that the number of groups is the same, that the sizes of the groups are the same as well, yes? Which means basically that I can assume that all those input graphs are on the same vertex set. They are just characterized by different edge families. Yes? Good. And again, by copying instances if necessary, I can assume that the number of instances is a square. It's a perfect square. Before, it was usually a power of 2 because I was encoding binary encodings, and now I'll be encoding pairs, so this is a square. So t, the number of instances, is s squared for some parameter s. Good. Okay, so this is the construction. So we started with instances looking like this, and now on each side, A and B, yes, I copy the corresponding side A s times. Yes, so I've got 1, 2, 3 copies. 1, 2, 3 copies of the left side and the right side. Now I put some connections that are non-trivial, that were not in the original graph. Namely, each group individual in each of the copies will be turned into a clique. Yes? And moreover, I put like full bipartite graphs that are symbolically depicted here between every 2 different groups. Yes, so there are all the possible edges between here and here. Yes, and all possible edges between here and here.
Sorry, what are you talking about, the left side and the right side, but you are putting your pentagram graph in up and down. So I missed something.
Okay, maybe left is up and the right is down. I'll try to say up and down from now on. Yes. So I've got the upside and the downside. Yes. Yes. All of those graphs are just different edge sets on exactly the same vertex set. Yes? And I've got t of them. Yes? And now I would like to create one instance of vertex cover, yes, on possibly a larger graph. Yes? So what I do, I copy each of the sides, the upside and the downside, s times. Yes? And the idea is that now, because I've got s guys here and s guys here, s copies here, I've got s square pairs of copies. So each of the pairs of left side, right side will be like a placeholder for one of the input instances. Yes? Good. So the connections. I make each of those a clique, and I make all possible connections between different copies. Yes? And now I embed the instances. So I've got s square instances and s square pairs. So what I do for every pair of upside and downside, yes, I embed here exactly the edge set, but the complement of it. Yes? I just put an edge whenever there was no edge, and I put no edge whenever there was an edge. And this is my instance. Okay, so now how this works. Now I will ask whether this graph has a vertex cover of size n, which is the total instance size, minus 2k, which is equivalent to asking whether it has an independent set of size 2k. Right? Okay, so how does such a vertex cover size 2k work? I cannot take any vertices from two different copies on this side, because they are connected by an edge. So all the vertices I take need to be from one copy, on this side and on this side. Moreover, I cannot have two vertices from the same color, from the same group, because this is a clique. So in order to pick 2k vertices for an independent set, I need to pick one copy here, and pick one vertex from each of the groups. And now, in order for this to be an independent set with respect to the edges between, yes, in the complement, I need this to be a BICLIQUE. Yes? And that's the end of the story. Yes? So the parameter of the output instance, the size of the vertex cover I'm asking for, is like n minus 2k. Yes? But the whole size of the output instance was like square root of t times a polynomial in the maximum input size. Yes? So this is allowed, meaning this is the parameter we are shooting at. Yes? So this is a recomposition of dimension 2, so I do not have any subquadratic compression. Okay, so now if I have already hardness for vertex cover, I can again play the same game. Apply reductions. Yes? For example, for feedback vertex set, remove at most k vertices to get a forest. There's a very simple reduction from vertex cover that goes like this. Whenever I have an edge in the original graph, I just add one more vertex like this, thus getting a triangle. Yes? And now in order to kill this free cycle, I need to kill either this vertex or this vertex. Yes? So this is a linear reduction from vertex cover to feedback vertex set. So, for example, feedback vertex set also doesn't have a subquadratic kernel. Yes? So if you look in the literature, there are more lower bounds like this, mostly for the problems for which we gave already some kernels using sunflower lemma. So like packing sets, hitting sets, and so on and so on. So let me not go into the details. Okay. So in the last, say, 5-10 minutes, I wanted to tell you about Turing kernelization, which is another different paradigm of kernelization, which I think is kind of important nowadays to know of, because it's conceptually a little bit different and it's very interesting. So the standard notion of kernelization is based on sort of this so-called many-one reductions or carp reductions. Yes? I take one instance of the input problem and I want to transform it into one instance of the output problem. Yes? But basically the premise of kernelization is that solving small instances, yes, should be simple. Yes? And basically we want to solve the whole problem by reducing it to some small core and solving a small core. Yes? But maybe we can reduce it to multiple small cores. Yes? Maybe just whenever we have on our way some small instance, we can apply our brute force algorithm to say that it is solved. Yes? So it is quite restrictive to say that kernelization needs to output just one instance. Yes? So then you can make this notion of Turing kernelization, where you can not just output one instance, but you can iteratively ask for solutions for small instances. So formally, a Turing kernel for a parameterized problem is a polynomial time algorithm that solves the problem, but which is given an oracle access. Yes? Which is given an access to an oracle. The algorithm can define an instance of size at most p of k and ask the oracle whether the answer is yes or no for this. Yes? So basically, the polynomial time algorithm on its way can solve small instances. Yes? So of course, a normal kernel is also a Turing kernel, because I can just apply kernelization and ask the oracle one question at the end. Yes? But maybe possibility of asking more questions on the way gives us more computational power. Yes? So the answer to this question is that yes, it does, meaning we do have examples of problems that have Turing kernels, but do not have provably normal kernels, but we don't understand it, meaning we don't understand complexity lower bounds for Turing kernelization. Okay, so one example that I would like to show you of this phenomenon is the max-leaf problem. So given a graph G and an integer k, does the graph have a subtree, a subgraph that is a tree, that has k leaves? Yes? So this problem doesn't have a polynomial kernel. It is NP-hard, and disjoint union gives you an OR composition. Because a graph has a subtree with k leaves if and only if any connected component has. Right? On the other hand, max-leaf on connected graphs has a linear kernel. To see it, it's actually not that magical. There is a very nice theorem of Kleitman and West in exponential graph theory that says that if you have a graph of minimum degree 3 that has at least 4k vertices, then for sure you have a spanning tree with at least k leaves. Yes? And now, if you have a graph where you can have vertices of degree 1 and 2, they sort of can be reduced. The idea is that basically, if you have a graph that has less than 4k vertices of degree 3, then these are those less than 4k vertices of degree 3 joined by long paths of vertices of degree 2, maybe with some out-hanging trees of vertices with degree 1 at the end. Yes? And this you can reduce quite easily. Yes? So the corollary is that this max-leaf problem actually has a linear Turing kernel, because what I can do, I can just look at every connected component separately, and I can just apply my oracle kernelization there and ask the oracle about this connected component separately. Yeah, so I make n oracle calls at most. Good. So this is a so-called OR Turing kernel, yes, which means that basically the algorithm only prepares some number of instances and then asks the oracle about the OR of those instances. Yes? There are other examples. For example, k-path that we already worked with, but on planar graphs. This has actually also a Turing kernel, and this one is truly adaptative in the sense that the next oracle calls depend on the answer from the previous ones. Yes? Good. Okay, so just to conclude, I think that this is a nice moment to wrap this whole kernelization part that was given today. I would like to mention some open ends of kernelization. So some problems that are known to be hard that you can think about. So some concrete open problems that are hard in the field of kernelization. First and foremost, I think that directed feedback vertex set should be here. Namely, you are given a directed graph, integer k, delete at most k vertices to get a acyclic directed graph. This is a notorious hard problem in parameterized complexity. It is FPT for very non-trivial reasons. And its kernelization state is open since the beginning of the days. Good. Another example is this multi-way cut problem. This is another cut problem. You are given a graph with a subset of terminals, and you want to pairwise disconnect the terminals from each other using deletion of at most k, say, edges. Yes? So this problem has a kernel with the number of vertices depending on t with the exponent, in the exponent. And whether this can be avoided is also a notorious open problem. No? Good. Another open problem from sort of a different family is this F-deletion problem, where you've got a finite family of graphs, yes? And this is like minor hitting problem. These are forbidden minors that you would like to avoid. Yes? So say, if avoiding K33 and K5, the Kuratowski graph, yes, means trying to make your graph planar. And I want to make your graph planar or make your graph F3 or F minor 3 by deleting at most K vertices. Yes? So this has a polynomial kernel if F contains at least one planar graph. But this makes the problem very different from the original problem. Yes? And whether for any F this has a polynomial kernel is an open problem. So these were the concrete open problems, but I would like to mention also some directions that people are pursuing in kernelization and in kernelization lower bounds. And I think that the main direction that is not really pursued now but should be is the framework explaining the limitations of Turing kernelizations. Yeah, because we now have a scattered set of various problems for which we know that there are Turing kernels but no normal kernels, and we sort of not understand why. Yes? And getting some good grounded in complexity theoretical assumptions framework for excluding polynomial kernels is definitely a big challenge. So here, one thing that you could do is to try to make a complexity theory for kernelization, to make a nice notion. We have a nice notion of reduction of PPTs, yes, and therefore this preserves existence of Turing kernelization. So if you don't know what to do in complexity theory, you assume something and build a complexity theory on some notion of reductions. So people have already done this, but this sort of was not pursued any further. There's lossy kernels about which you will hear a lot further, and also there's a direction of bounding the resources for kernelization. So, for example, if you aim at a FPT algorithm at the end of the day that runs in linear time, yes, then if you want to apply kernelization in the middle, you'd better have this kernelization run in linear time. Yes? So, for example, you can ask about linear time kernelization. Or, in the world of big data, you can ask about streaming kernelization. Yes? So, basically, the kernelization algorithm needs to pass through the data several times, keeping only a bounded number of information at the moment. Yes? And thank you for the attention.